set of notes. And we're going to talk about, first off, the setup for an exponential function. And here we have the basic form for an exponential function. It says that if a is greater than 0 and if a is not equal to 1, then an exponential function is defined as f of x is equal to a raised to the power of x, where a is your base. Now, in algebra, we talk about variables, and it would appear, just based on this setup, a raised to the power of x, that both a and x are variables. However, the only variable in this exponential function is x, right? A is some type of number. All right, so the only variable is x. For example, if we were asked which is an exponential function, and I'm just going to write a, which is y is equal to x squared plus 4x minus 1. And let's say we have b, y is equal to 2 raised to the x plus 5. Okay? And if you were asked which one of these things is an exponential function, if we take a look at a, right, y is equal to x squared plus 4x minus 1, notice that the variable x is the base of those exponential functions. Okay. So if we're looking at, let's say, the functions we've been looking at thus far, such as linear, quadratic, cubic, square root, rational, those kind of functions, the variables for those functions is the base. These are considered algebraic functions. Okay, so answer choice A is an algebraic function. If you take a look at, I'm sorry, that should be B, y is equal to 2 raised to the x plus 5, notice that the variable x is an exponent. Okay, and the base, which was once the variable in algebraic functions, is now some constant. So if you're looking at a function and your exponent is a variable, these are considered to be exponential functions. Okay, so that's how you would identify an exponential function. Okay, I'm going to go back to the notes for just a second. And there are two types of exponential functions. There is an exponential function in which your base a is greater than 1. So I'm actually going to pull up the calculator. And I'm going to graph some functions. So this is what's called a function capsule. And it just gives some background information about an exponential function. And it says an exponential function is in the form f of x is equal to a raised to the power of x, such that a, which is your base, has to be greater than 1. If your exponential function fits this case, the domain is always negative infinity to positive infinity. The range is from 0 to positive infinity. If we take a look at the graph, As we read this graph, right, we read graphs from left to right as we read sentences from left to right. Notice that this graph is increasing. Okay. And that would be true for any exponential function whose base is greater than 1. Okay. Also, some more facts about the exponential function whose base is greater than 1. They would pass through these points. -1 comma a to the negative first power. They will always pass through the point 0 comma 1, and they will always pass through the point 1 comma a. Every exponential function has a horizontal asymptote. Okay, so that horizontal asymptote would be the horizontal line that your graph gets closer and closer to but never actually touch. All right, so I'm going to just pull up the calculator. And I'm going to just clear out those functions. So for y sub 1, I'm going to put in 2 raised to the power of x. And I'm going to hit zoom 6 to graph. So notice that in this function, f of x is equal to 2 raised to the power of x. So notice that for this example, a would equal to 2, right? So if I go back to our little function capsule, notice that these points from this first given thing here, I don't know if you can see if I'm circling or not, I would simply substitute a for 2, right? So the first point that would have to fall on this line is -1 comma a to the negative first power. So that would be -1 comma 2, because a is 2 to the -1 power, and 2 to the -1 power is actually 1/2. So I would have the point -1 comma 1/2 on this graph. I would also have the point 0 comma 1 on this graph, and I would also have the point 1 comma 2. Just to verify that, I'm going to use a calculator, and I'm going to go into table, which is right above graph. So I'm going to hit second and graph, which gives me the table. All right, and notice the points that are on the line. We have -1 comma 1/2, right, which is 0.5. We have the point 0 comma 1, and we also have the point 1 comma 2. Now, just to make sure everyone is clear on these negative exponents, because we will deal with negative exponents. Here is a negative exponent rule. It says that a to the negative n is equal to 1 over a to the positive n. So for example, if we have 2 to the negative first power, I can write that as 1 over 2 to the positive first power, which is actually 1/2 or 0.5. So if we take a look at that graph, we see that -1 comma 2 to the negative first power, right, which is actually 1/2 or 0.5, is actually a point on our curve. Now, what if the base is something that's not greater than 1? So here we have our second setup for an exponential function. The base is greater than 0 but less than 1. So as we go further, just notice two things. The base for an exponential function can never be negative, and the base for an exponential function can never equal to 1. Right? The base either has to be greater than 1 or it has to be in between 0 and 1. So let's take a look at the second setup. So here we have the same exponential function, f of x is equal to a to the power of x, but notice that our base a is greater than 0 and less than 1. So the domain is still all real numbers, and the range is still the same from 0 to infinity. But notice the graph. As you read this graph from left to right, this graph actually decreases or descends, where the other graph, as you read it from left to right, it increased. So if your base is in between 0 and 1, then your graph is decreasing. And here's some facts that follow that. Here's the points that would lie on the graph. -1, comma, a to the negative first power. 0, comma 1 is a point on the graph, and then 1, comma 2. So to see an example of this function, I'm going to go back to y equals. I'm going to clear that out, and I'm going to put in 1/2, right? Because that's a number between 0 and 1 raised to the power of x. And if we graph, notice that the graph descends from left to right. Okay. And if I were to just check our points, so I'm going to go back in the table. All right, so we see the point -1, comma a to the negative first power. So let's say I have 1/2 raised to the negative first power. What actually happens? Now I'm going to use the negative exponent rule, and I'm going to flip-flop my fraction. 1/2, I'm going to write it as 2 over 1, but my exponent becomes positive 1. Right? So 2 to the first power is actually 2. Okay, so that is the negative exponent rule, right? So I actually have that point on my graph, right? -1, right, which is here, comma 1/2 to the negative first power, which is actually 2. So I have that point on my graph, -1, comma 2. I also have the point on the graph 0, comma 1. And I also have, how did that go back? 1, comma a. So remember, a was 1/2 of 0.5, and I have that on my graph, 1, comma 0.5. All right. The main things I want you to keep in mind is that when you are asked to graph, I would graph using a graphing calculator, and then I would go into the table, and then I would just pick these points as points to use in XYZ homework. All right, so with that being said, let's evaluate an exponential function. Okay. So the directions here are to evaluate. So let's say we have f of x is equal to 3 times 6 raised to the x power, and we want to find f of negative 3, right? Right, so I'm going to pull out the calculator. I'm basically going to enter in what I see. Okay. I'm going to put in 3. I'm going to put in the begin parenthesis. I'm going to put in 6, and I'm going to raise that with the caret to x, and we're substituting x with negative 3. Since the exponent is negative, I'm going to encase that exponent in a set of parentheses. Right, so I'm going to put in negative 3. And let's say if we round to 4 decimal places, we have 0.0139. All right, let's take a look at another example. F of x is equal to negative 5 raised to the 3x plus 3 power. So I'm going to do the same thing, but I'm going to do it in a slightly different manner. I'm going to go into y equals, and I'm going to put in that function negative 5. I'm going to raise that. And I'm going to use the begin set of parentheses to the 3x plus 3 power. And I have that function stored as y sub 1. And I'm going to go back to the home screen. Now I am going to, let's say we're going to find f of negative 3. All right. So this is just a second method. You could just substitute negative 3 for x, right? Put it in this home screen and solve it. Or you could put it as y sub 1, right? And I put that as y sub 1. And now I'm going to actually recall that y sub 1 function. So I'm going to go into variables, which is VARS. And I'm going to put some steps. So the first thing I did was enter the function in y equals. Then after you put your function in y equals, you want to return to the home screen. And the home screen is second and y equals. Right, now return me to this home screen. Excuse me, second and mode, I'm sorry. Now we want to recall the variables, so we're going to hit vars. I'm going to scroll over to y variable. I'm going to hit, okay, and then we want function. Then I want to hit enter. Okay, and from this point, we want to choose the function, and we've stored that function in for y sub 1, so I'm going to hit enter. All right, so notice that y sub 1 pops up, and now we want to substitute in the given value, so I'm going to hit -3, but you must use a set of parentheses. All right, so I'm going to evaluate the function y sub 1 at -3, and if you hit enter, this is what we get. -6.4 times e to the -5th power. And I want to explain this one to you. Now, I believe this was similar to the second one. Now, as far as the directions, they want us to round to the nearest, or round the 4 decimal places. All right, so this e that you see pop up in your calculator, that means times 10. Right, so -6.4 e is -6.4 times 10 to the -5th power, right, which is actually exponential. Well, it's actually scientific notation. This -5 means that we need to move this decimal place 5 places to the left. So I'm going to move it once. That puts it in front of the -6. 2, 3, 4, 5. Right, I'm going to fill in those 4 zeros. Right, and if we were to round to the nearest 4 decimal places, we would get 0.0001. All right, because if I look one place to the right, that -6 is larger than 5, and this would be negative. And I have -0.0001. All right, when in essence would be 0. All right, 0 is neither negative nor positive. So just 2 methods on how to evaluate exponential functions. You can simply directly substitute the number in, or you can put it in y equals and evaluate it through the function itself. All right, now we're going to talk about solving exponential functions. I want to go back to the slides for just a second. And I want to talk about these additional properties of exponents. All right, so we have looked at the negative exponent rule, right? A to the -n is equal to 1 over a to the positive n. I want to look at B on this additional properties of exponents sheet, and it says that if a raised to the power of b and if a is raised to the power of c, then you can set b equal to c. So in layman's terms, that means if your bases are the same, you can drop the base, set the exponents equal, and then solve. All right, so this is the like base property. Right, so if you're asked to use the like base property, this is what they're referring to. It says that if a raised to the b is equal to a raised to the c, then you can set b equal to c. So let's actually see that in action. Okay, we'll start with some simple ones. So let's say we have 2 raised to the power of x is equal to 2 raised to the power of 3x minus 4. So notice that this is an exponential function or equation because it contains an equal sign. And notice that the variables are in the exponent area. The like base property says if we have like bases and both of these exponential functions have a base 2, we can drop the base and set the exponents equal. So I can actually drop my base and I can write this as x is equal to 3x minus 4. So we have switched this from an exponential function to an algebraic function. And now we can just solve it for x. So in order to solve for x, I am going to subtract x from both sides. And I'm going to add 4 to both sides. Right. So I guess to write out some steps. First thing I'm going to do is add 4 to both sides. So I'm going to add 4 to the left-hand side. I'm going to add 4 to the right-hand side. Right, the properties of equalities tell us whatever we do to one side, we do the same thing to the other. So on the left-hand side, we have x plus 4. On the right-hand side, we have 3x, right, because the 4s are canceled. The next thing I'm going to do is subtract x from both sides. So I'm going to subtract x from the left-hand side. I'm going to subtract x from the right-hand side. So on the left-hand side, the x's will cancel. I'm left with 4. On the right-hand side, 3x minus x is 2x. And now I can solve for x. I'll divide both sides by 2. So x is equal to 2. Now I can also check. Okay, now checking is not necessary, but going through this first example, we're going to check. So how we check is we take our original function and I'm going to substitute x for 2. All right, so wherever I see an x, I'm going to put a 2. So we have 2 raised to the power of x, so we're going to substitute x for 2. That's equal to 2 raised to the power of 3 times x, which is 2 minus 4. On the left-hand side, 2 squared is 4. Right. On the right-hand side, my base is still 2. So I'm going to simplify my exponent. 3 times 2 is 6. Bring down to minus 4. Right. So 2 would be the magic number that makes both sides equal. All right? So you are able to check your solution. So now let's look at some other examples. 1/2 raised to the x minus 6 is equal to 2 raised to the 3x plus 8 power. And we are asked to solve. So now from the way the probability is given, and they want us to use like basis. So as the problems are set up, as a problem is set up, I don't actually have the same base. One is a base 1/2, one is a base 2. So I can either do one or two things. I can make them both base 2s, or I can make them both base 1/2. So I'm going to make both of these things have a base of 2. Okay. So now on the right hand side, that already has a base 2, 2 raised to the 3x plus 8. I can actually write 1/2 as a base 2 using the negative exponent rule. So if I go back up just to show what we did. Okay, right here, I can actually write 1/2 as a base 2. So notice for this example, we had taken 1/2, and if you raise 1/2 to the negative first power, right, that gives you 2 to the first power, which is 2. So I am going to do that here. I'm going to rewrite 1/2 as 2 to the negative first power times x minus 6. And I want to explain or review another rule for exponents. It says that a to the m times a to the n is a to the m plus n. And also a raised to the nth power raised to the m power is a to the n times m power. So for this first property, a to the m times a to the n is a to the m plus n. Whenever you are multiplying like bases, you add your exponents. The second one says a to the n times a to the m. So you're taking a power and you're raising to a higher power, right? Because we have a that's raised to the power of n. We're raising that to a higher power, which is m, so we're going to multiply. So we're actually going to use that second property for this. I'm taking 2, which is raised to the negative first power, and I'm trying to raise it to the x minus 6 power, so I'm going to multiply. I'm going to multiply -1 times x and -1 times -6. Right, so I'm going to rewrite the left-hand side as 2 raised to the negative x plus 6 power is equal to 2 raised to the 3x plus 8 power. And now we have like bases. So I am going to use a like base property. I'm going to drop the base, and I'm going to set the exponents equal. And now we're going to solve. All right, so I'm going to add negative x. We'll add x to both sides. I'm going to subtract 8 from both sides. I'm going to divide both sides by 4, so x is equal to negative 1/2. So now if we were to check, right, negative 1/2 would be the number that makes both sides of that exponential equation equal. All right, let's take a look at, okay, I have a couple more. Seven raised to the 4y minus 2 power is equal to 343. All right, so here again, we want to use the like base property. So I can actually make both of these a base 7, right? I believe 343 is 7 cubed. All right, so just to verify that, 7 raised to the 3rd power is 343. So I can rewrite 343 as a base 7. So here we have 7 raised to the 4y minus 2 is equal to 7 raised to the 3rd power. I have like bases, so I can set my exponents equal. 4y minus 2. 4y minus 2 is equal to 7. Right, and we can solve. So I'm going to add 2 to both sides. 4y is equal to 9. I'm going to divide both sides by 4. Y is equal to 9/4 as our solution. And I'm going to make a slight correction. I did something wrong here. On the right hand side, that should actually be a 3 because I dropped my base, right? So that's 4y minus 2 is equal to 7 to the 3rd power. So I'm going to drop my base, which is 7. So this should equal to 3. All right. So I'm going to add 2 to both sides. 4y is equal to 5. Divide by 4, so y is equal to 5/4. So if you're ever unsure about your answer, you can check. All right, and we will take a look at one more. Okay, this is 1/16 raised to the 3a power times 32 is equal to 2 to the 4th power. All right, so here again, our job is to make everything have a like base. So we're going to make everything a base 2. All right. So just by looking at this, I know that 32, that's 2 to the 5th power. And I have 2 to the 4th power, which is already a base 2. So I want to rewrite 1/16 raised to the 3a power as a base 2. So we're going to use that negative exponent rule. So I'm going to do that on the side. A to the negative n, that's equal to 1 divided by a to the positive n power. And then this is vice versa. Which is actually how we're going to use it. So we have 1/16, right? 16 would be 2 to the 4th power, right? So just to verify that, 2 raised to the 4th power is 16. But since we have 1/16, that's 2 raised to the negative 4th power. Okay, so just to show that on the calculator, 2 raised to the negative 4th power is 0.01625. If I change that to a fraction, I get 1/16. So I'm going to substitute 1/16 for 2 to the negative 4th power, and that still is raised to the 3a power. All right, so if we look at that first factor on the left-hand side, we have 2 to the negative 4th, and we want to raise that to the 3a power, so I'm going to multiply. So that's 2 raised to the negative 12a times 2 to the 5th power is equal to 2 to the 4th power. All right, now keep in mind the couple of rules we just talked about. I'm going to go back here, and I want to concentrate on this one. A to the m times a to the n is a to the m plus n. So if you're multiplying like bases, you should add your exponents. So going back to our problem, I'm multiplying 2 to the negative 12a times 2 to the 5th power. So I'm going to add those exponents. So I'm going to write this as negative 12a plus 5 is equal to 4. And now I'm going to solve. Right. So in order to solve for a, we're going to subtract 5 from both sides. So we have negative 12a is equal to negative 1. I'm going to divide both sides by negative 12. So a should equal to 1/12. All right, so for here we had to use the fact that if we are multiplying like bases, we add the exponents. Right, and here is the last example. 16 raised to the 3x plus 5 is equal to 4 raised to the 4x plus 1 power. All right. All right, so I'm going to try to rewrite both of these as a base 4. All right, so notice that the right-hand side is already a base 4, so I'm just going to bring that down. I can rewrite 16 as a base 4. Right, 16 is 4 squared. Right, so I'm simply replacing 16 with 4 squared. Now it's a base 4 raised to the 3x plus 5 power. So now since we're raising a power to a higher power, we want to multiply. So I'm going to multiply 2 times 3x and 2 times 5. So here we have 4 raised to the 6x plus 10 is equal to 4 raised to the 4x plus 1. We now have a like base of 4, so we're going to drop base 4 and we're going to set our exponents equal. 6x plus 10 is equal to 4x plus 1. And now we're going to solve for x. So I'm going to subtract 4x from both sides. So I have 2x plus 10 is equal to 1. I'm going to subtract 10 from both sides. So now we have 2x is equal to negative 9. I'm going to divide both sides by 2, so x is equal to negative 9/2. All right, so negative 9/2 would be the magic number that makes both sides equal. So I'll just check this one. Just to show real quick. So I'm going to use that little variable method to check this. I'm going to go into y equals. And I'm going to clear that out. I'm going to put in 16 raised to the 3x plus 5 power. I want to go to y sub 2. I'm going to put in 4 raised to the 4x plus 1 power. I'm going to go back to the home screen. I'm going to pull up that y sub 1 equation. I'm going to evaluate it at negative 9/2. I'm going to pull up y sub 2. I'm going to evaluate that at negative 9/2. And I should get the exact same number value. Okay, so that means that both sides of that equation are equal.